at my end. But maybe I'm not supposed to inside Zoom.
I can see the live stream now. Okay, hello and welcome everybody to today's Saturday morning lecture, which is the third of 4 events this fall. My name is Stanley Yen. I'm a research scientist at Triumph, and I will moderate today's session. This year, because of COVID, our lectures have gone online, and despite the difficult circumstances of this past summer, we were blessed to have seen a bright naked-eye comet, Comet NEOWISE, which is a once-in-a-decade occurrence. So it is timely to hear a talk today from an expert on comets. Our speaker is Professor Brett Gladman from the Physics and Astronomy Department at UBC. His research interests are in the field of formation and evolution of planetary systems. In the live stream description, you will find links to learn more about our speaker's career and accomplishments. During the lecture, I invite listeners to submit questions in the chat box in the YouTube live stream. At the end of the lecture, these questions will be submitted to the speaker during the question and answer period. So now I invite Brett to speak to us about comets, magnificent messengers.
Hello, everyone. Thank you for coming out on a Saturday morning, or at least tuning in on a Saturday morning. So today I'm going to talk to you about some historical context about comets and leading up to a better understanding of the Majestic site we had in our skies earlier this year related to this particular comet NEOWISE. It's interesting to note that until the 18th century, our understanding of our solar system was much more restricted than currently. In fact, there were only a handful of things that humanity knew about in the solar system. So there was the sun with the classical planets Mercury, Venus, Mars, Jupiter, and Saturn, the wanderers, moving in the sky, which has been, these objects have been known since antiquity. Because the telescope had been invented, in addition to our moon, we had observed the largest moons of Jupiter and Saturn, the Galilean satellites, and Saturn has some large satellites which are easily visible in a telescope circling them. And basically that was it. Those were the only objects where you would say, oh, I want to go observe X, and you could go look. In addition to that, every now and then, making brief flashy appearances, there were comets that appeared in the sky, apparently randomly, put on a big display for a period of weeks, and then disappeared, never to be seen of again. And a really bright comet of the kinds that have happened historically are truly impressive sights that can cross a large fraction of the visible sky, lighting up our heavens. The basic morphology is that there's a head, or a nucleus as it's called, and a very long tail. And when you look at a picture like this, it can be hard to judge how far across the sky the tail is. Here's a woodcut from an ancient comet over a European city, showing the tails extending tens of degrees across the sky. And these would be the largest, most expansive things anybody had ever seen in the sky. Because of that aspect of appearing and then disappearing, historically, many cultures took these as omens, either of good or bad. It is said that the appearance of a comet in 1066 was viewed by various parties as an omen, which heralded the invasion of England in 1066, is recorded here famously in the Bayeux Tapestry, with the comet that we now understand is Halley's Comet in the sky. And in fact, it was Edmund Halley who, in 1705, based on the properties of a comet that was seen in 1682, believed that that comet was actually a reappearance of the same comet that appeared in the sky 76 years earlier in 1606. And based on that, he believed that same comet would return in 1758. Halley didn't live to see that return, but this 1758 comet, which now bears his name as Halley's Comet, was the first predicted return. So it was realized that some comets are so-called periodic comets. They're in orbit around the sun on large orbits that bring them back around periodically. And in fact, if you work this backwards, the 1066 comet is also Halley's Comet. So when a comet appears in the sky, that particular episode is called an apparition. And because the comets orbit the sun, the apparitions occur when the comet gets really close to the sun and lights up via processes that we'll talk about in a few minutes. Halley's Comet is actually retrograde going around the sun. So that means in this view, looking down on the plane of the planetary system, the planets are all going around counterclockwise from our perspective. And Halley's Comet actually goes the other way every 76 years. And so it's showing that it was near the sun in 1910, 1986, and will again be in a few decades. Exactly how impressive a given comet is on a given apparition depends heavily on the orbit of the comet, and when it comes to its closest approach to the sun, where it will be the most active and have the largest tail. What matters is very much where in this diagram you can see the somewhat viewed edge-on circular orbit of the Earth. And if the Earth is near the comet on the same side of the sun, then the comet will be close and very bright in the sky. Halley's 84 apparition was not particularly, oh, that should be 1986, excuse me, that's a typo. That apparition, unfortunately, the Earth was on the opposite side of the sun, and so that was not a particularly favorable viewing geometry. On other geometries, Halley is here and Earth's around on the same side, like it was in 1910, and very spectacular. So what exactly are these objects? For a long time, humanity had no real conception of the scale of what these objects were. We now understand that comets are almost all just a few kilometers across. They're small objects. Historically, people wondered if they could be quite large because, as we'll see, the scale of their tails is huge. But skipping over that historical evolution, we now understand that comets are small objects that condensed in the early protoplanetary disk of material that was swirling around our young protostar. And once the protosolar nebula collapsed, it began to cool. And at different distances from the sun, the nebula was different temperatures. So much as if you take a pot of boiling water with sugar in it and let it cool down, and eventually the sugar begins to crystallize, solidify, and fall out of the liquid phase. As the protosolar nebula cooled and reached an equilibrium temperature depending on how far away from the sun it is. So here in this diagram, the Earth is here at 1 astronomical unit. That's the reference distance of the Earth-Sun distance. Okay, this is where the present locations of the planets are. And based on observations of our own solar system and these disks around other stars, this temperature profile, which was roughly 2,000 degrees by the time you got close to the sun, dropping down to just tens of degrees Kelvin above absolute zero out near the present orbit of Pluto, you have a profile like this of cooler and cooler temperatures. And the objects which froze out in the outer regions of the solar system, it was sufficiently cold that out of the disk you got not only the metal rocky materials like those which dominantly make up the terrestrial planets Mercury through Mars, but you also got a lot of ices condensing as solid, that it was simply too warm in the interior of the nebula for them to condense into solid form. And so that stayed in gas phase and didn't appear in the objects that then solidified by growing together. In the outer part of the system, though, you got icy rocky material. So this is a schematic of that process of planetary formation in which an enormous cloud of interstellar gas and dust collapses, spins up, and flattens into a disk. As it cools in the inner region, you get rocky things that are like asteroids that are the building blocks of rocky planets like the Earth and Mars. And in the outer portions of this disk, you get objects that we now understand are basically like comets. They're mixes of rock, but they're roughly half of their mass is in ice as well. Okay. Out of these materials, you then build the giant planets and the terrestrial planets in closer, and then you disperse many of the remaining objects. And the comets are objects that were formed in this early protosolar nebula that never got incorporated into the planets and have been stored. We can study these directly in some sense, because as comets lose material in their approaches to the sun, they leave behind abundant amounts of dust that the Earth plows through. And if you fly an airplane way up in the Earth's stratosphere with basically sticky tape on the wings, you can collect interplanetary dust particles that look like this. So this is about 1/10 of a millimeter across, this picture taken with a microscope. And it shows this very twisted aggregate of dusty, icy material that's in the, was collected in the upper atmosphere. And this is basically a piece of a comet that's come off in the tail of a comet during cometary activity. So the surface of the comet has piles of stuff that looks like this. And the bulk of the comet you could think of as a dirty snowball, i.e. good Canadian analogy, if you imagine at the end of winter beside the road as the snow is melting away and you get to that kind of unpleasant point where it's half dirt and half ice. If you were to make a snowball out of that, you'd have something that macroscopically looks like a comet, with the exception that the comet's ices are not just water ice, but that can have carbon dioxide ice and methane ice and ammonia ice mixed in with the rocky materials. For comparison, this is a recent picture of the asteroid Bennu, which you may have been reading about in the press. This is an escaped main belt asteroid, which is being visited by a spacecraft. And you see it looks like a big rocky pile of rubble, and that's in fact what astronomers call these rubble piles, with material of lots of different scales, from fine-grained dust ranging up to boulders you can see sitting here on the surface. Here's a couple of pictures of comets. Okay, the one on the left is actually the nucleus of Halley's Comet, and the one on the right is a different comet. The difference between these two pictures is the comet in the upper right. This picture was taken when the comet was very far from the sun and inactive, whereas Halley, this was right near perihelion, and a bunch of spacecraft were sent to fly by the active nucleus during close approach to study it. Okay, so I'll come back to Halley's picture here. So if you compare the surface of this comet, which is called Wild 2. So comets, by the way, are named after their discoverers. So this is the second comet that Mr. Wild discovered. It's 5 kilometers across. When you look at the surface, you see these depressions in the comet. And although you might think that perhaps those are craters from impacts like you see on rocky objects, these are actually probably the portions of the surface which are active. So if I go back to the Halley picture here, these are portions of the surface which are actively jetting material out as the solar heat vaporizes it. And these are probably where the comet was most active at its last perihelion passage. And it's basically eaten down into the comet. Okay. Here's another comet that was visited by a spacecraft. The European Space Agency built the Rosetta probe to go out and follow an incoming periodic comet, in this case, 67P. Halley is 1P, the first periodic comet. This is 67P, the 67th periodic comet, and everybody calls it CG because the full name is Churyumov-Gerasimenko, after the co-discoverers. Okay, and this object was followed in towards the sun before it got active, so that one could gradually watch the surface become active. This shape you have to be a little bit careful of because of the lighting. Okay, the sunlight's coming from the top here, and you can see this large depression here, which is in shadow. This is another depression which is in shadow because of the lighting. Okay, but the fact that the comet is bilobate. In other words, it seems to have a big main mass on the left and a smaller main mass on the right connected by a neck. That bilobate structure appears to be reasonably common in comets. Okay. This was visited by, as I said, a spacecraft, which stayed near it for a long time, getting these incredible pictures. So if we zoom in on this patch on the lower left, you can see that the surface of Comet is quite fascinating topographically. It has these areas with scattered boulders in the low-lying regions, which are lying on what appears to be these smooth areas. And these smooth areas are smooth because, in fact, they are the lowest points gravitationally and topographically nearby. And so when fine material is generated on the comet, just like if you have a bucket of sand that's got pebbles and bigger rocks in it and you shake it, all the sand will settle to the bottom. And that's what's going on here. On the surface of this comet, you have these low-lying regions filled with very fine material and thus look smooth from a distance. And there's larger objects sitting on top of it. Okay. If you remember this particular comet, this was a comet where they attempt to put a lander on the surface. So there was an orbiter that's not pictured, and this was a picture of the lander that is going to try and land and then harpoon the surface and study the surface material in situ. But unfortunately, the landing failed, and there was a period of, they got a few pictures back from it before it ran out of juice from its solar panels, unfortunately. That was 6 years ago. Okay, so how do we compare comets and asteroids? Well, both of them are minor planets in the modern terminology. So we have the major planets, we have the minor planets. Okay. The comets, which were discovered, the asteroids, which began to be discovered at the beginning of the 19th century. Most of them orbit in the famous main asteroid belt between the orbit of Mars and Jupiter, and they're the rocky planetesimals that didn't get incorporated into planets. They have small amounts of metal. They have hardly any water. All of those facts are believed to come from their location of formation in the protosolar nebula. And if any of them escape from the main asteroid belt, you get the famous near-Earth asteroids, which are the ones which generate the heavily discussed impact hazard on the Earth. Okay, so most of the impact hazard of something largest striking the Earth comes from escaped asteroids from the main belt that get into Earth-crossing orbits. Comets, on the other hand, are more messengers from the outer solar system, as we've seen. The active ones are on big eccentric orbits, which means they come inside the Earth's orbit, and their furthest distance from the sun, their aphelion, is at or usually much beyond Jupiter. And it's only at the portion of their orbit near the sun where they brighten and become active. The most distant examples we know can go out as far as 50,000 times the Earth-Sun distance at the edges of the Oort cloud, which I'll come back to in a moment. Okay, so there are two reservoirs of these comets because these comets can't be doing their cometary activity for the age of the solar system. They would have eaten themselves down to nothing. So there must be reservoirs. So first I'm going to talk a little bit about the cometary activity cycle, and then we'll return to these reservoirs. So on these big looping orbits, so here's a cartoon with the Earth's orbit shown for scale with the outcoming solar radiation and sometimes the solar wind, which consists of charged particles that are flowing away from the sun in addition to light. Okay, if we think about the comet here at the right, beginning at aphelion, as it comes towards the sun, the increasing intensity of the solar light begins to gradually warm the surface. And depending on which ices are sitting near the surface of the comet, somewhere around 5 astronomical units, the comet will begin to activate, and there will be a small amount of vaporized material beginning to come off the comet, and that's called a gas coma. but that's not although many incoming comets are detected in this phase because they get a little bit fuzzy around them. It's when they get in closer to the sun at about the Earth's distance of 1 astronomical units that they really light up. And now, being closer, they're vaporizing more material. And due to the proximity of the sun, the solar radiation and solar wind pushes the tail away from the sun, producing this tail. There are two types of tails I'll come back to in a moment. Something that's a little counterintuitive is many people think the comet must be moving in the direction opposite the tail, but in fact, the tail's always being blown away from the sun. So as we return around the sun, the tail flips around and actually precedes the comet along its orbit, which is confusing for many people. As it heads back out into deep space, it cools down, and eventually the tail goes away, eventually back out at 3 to 5 astronomical units, the coma disappears, and it goes back into frozen cold storage, in which case it will look like that inactive comet Wild 2 until its next return to near sun space. Okay, so to establish the scale of this, down at the head of one of these comets, there is this little structure that's a nucleus that's only a few kilometers across. Okay, almost all the comets we've ever seen, to our knowledge, we're talking about the nucleus, which is the remaining part, solid part of the comet, once all the activities shut down, that's just 3 to 10 kilometers across. And if we look at this picture of Halley is about that scale. Okay, so this is just several kilometers across. As we've seen, only a small fraction of the surface is being heated by the solar incoming light, which is to the left in this picture. And at those places, you're vaporizing off dust, which is dust and gas, which is ejecting away from the surface of the comet. This was a very dangerous flyby. Several spacecraft did this. The one that was most successful was the European Giotto mission back in 1986, because you had to fly through the comet. And when you get this vaporization, there's dust as well. So there were dust particles striking the spacecraft at speeds of tens of kilometers per second, pelting it as it whipped past the comet to take these few pictures. Once that vaporization happens, it produces a tail, which is extremely fine material. There's really very, very little mass that's ejected in each orbit. So the tail consists of material that's coming off just the few upper meters or tens of meters of the comet that's boiling away and being pushed away. But because that material, because that dust reflects solar light, it has an enormous cross-sectional area. So this nucleus of a few kilometers, which is hidden at the head, invisible at this scale, is connected to this tail, which can extend hundreds of millions of kilometers. Distances comparable to the Earth-Sun distance, or an astronomical unit. So comets can be incredibly large on the sky, despite the fact that they have, in fact, very little mass, but that mass is very good at reflecting the solar light, which we can see. A detail which many of you will have noticed is it appears the tail has some structure to it. In particular, there's this bluish tail, which is called the ion tail, and the dust tail. So most of the tails in this neutral dust, which just vaporizes off and gets carried away. During that process, some of the dust picks up a small electric charge and is therefore feels the magnetic field of the sun, and that actually gets blown, therefore, perfectly directly away from the sun. So if you're looking at a comet picture like this and you want to know which direction the sun is, It's opposite this blue tail. It's off to the lower left, perfectly anti the direction of this ion tail. Okay. And it's that the ion tail actually has slightly smaller particles on average in it. So that what makes the tail straighter. It's just pushed directly away from the sun. So this is just another cartoon of the fact that as the comet comes by, the tail, especially the ion tail, points away from the sun. So how did these comets get to the orbits that we observe them on now? Because if you calculate the size of one of these comets, we typically think a comet could only go around the sun thousands or tens of thousands of times before it would have boiled away all the surface ices and gone extinct and not show cometary behavior anymore. And there are two reservoirs of the comets in the solar system, both of which many of you have probably heard of. One that we've only been able to study for 30 years is the Kuiper belt. Like the main asteroid belt, this is a ring of small bodies beyond the orbit of Neptune. Pluto is in the Kuiper belt. And that's one reservoir. Some comets have stayed in the Kuiper belt ever since they formed. They have been jostled free by the perturbations of the planets relatively recently in solar system history, and they're transferred down to orbits near the sun. In our outer solar system, between the orbits of Jupiter and Neptune, it's largely empty because the gravitational effect of these planets is able to discard any objects which might be here in a time scale that's much shorter than the age of the solar system. In particular, when you formed these four planets, there were doubtless trillions of small comets in this region that were participating in forming those planets. So this is a little cartoon time sequence. If we think of the protoplanetary disk, which sedimented out a huge amount of dust as it cooled in a flattened disk here seen edge on with the sun at the center. The sun's not even actually a real star yet at this point. It's a protostar. It hasn't ignited thermonuclear fusion in its core. So you formed the dusty little bits, and they form into objects that are we call planetesimals, and comets you can think of as basically icy planetesimals. Out of those planetesimals, you make the planets on an unclear timescale that's certainly less than a few million years. And once you have the giant planets that we have today, their gravitational effect is so strong that they clear the region between themselves very quickly. And even into the Kuiper belt beyond the orbit of Neptune, you erode some of that material. It turns out that the giant planets are very bad at sucking it into themselves. That is, their gravitational power is so great that they're much better at slingshotting the material out to large looping orbits away from the sun than they are at having the comets attracted in and absorbed by the planets. So because of that, here there's a dramatic change of scale, which I'll improve in the subsequent slides. You fling these objects out to distances of thousands or tens of thousands of times the Earth-Sun distance, which is hundreds or thousands of times the distances that the planets are at. And they form what are called the Oort clouds. So those objects which get flung out there, which are actually the planetesimals that are formed between the giant planets, they're stored there then for billions of years. And they're actually the unused building blocks that built the giant planet core. So we're very interested in studying them because they are basically condensations of the protosolar nebula that we can then study, and because they've been in cold storage for the whole age of the solar system before they come back. An interesting dynamical detail here is the reason that the storage works is they get pushed out so far that the gravity of the sun, although dominant, is not the only important force on them. And in fact, at those distances, these comets begin to see the gravitational effect of the disk of the galaxy. And the effect of that is to change their orbits slightly. And then at their closest approach, they don't dive back into the giant planets. And that's what allows them to be stored for billions of years. But there are other things in the galaxy too. And in particular, sometimes stars come by close to the sun. By close to the sun, we mean at distances comparable to the Oort cloud at tens of thousands of astronomical units. And those gravitational perturbations can modify the orbits of some of the storage comets and push them back into the planetary system. And that's how we get these visible comets. Okay, so this is the largest scale in the solar system. And as is typical in astronomy, that makes it extremely difficult to draw a scale diagram of. So I've got a couple here to try to get this immensity across. So on the right here, you see the orbits of the four giant planets, Jupiter, Saturn, Uranus, and Neptune, surrounded by this donut, which is the Kuiper belt, a flattened structure that's outside the orbit of Neptune. And this scale is 50 AU. The whole thing's a couple of hundred astronomical units across. Okay, so a few times the size of the giant planet orbit system. And then you have to condense that down by a factor of 1,000. So this diagram does not do it correctly. So microscopically at the center of this left diagram, there is the Kuiper belt, and it's surrounded by this structure, which is tens of thousands of astronomical units in radius. And there are roughly 1 trillion comets circulating here in cold storage. We can determine that by the how many of them come in per century from the exterior regions of the solar system. And we know there's a truly staggering number of little comets stored out in the Oort cloud, left over from the age of the solar system. Here's yet one more attempt to do a set of jumps in scale. So at the bottom here, you see the planets, just to have a picture where the planet radii are to scale to each other. But on the scale of their orbits, the planets are invisible. You have the terrestrial planets here, Mercury, Venus, Earth, Mars. Here's the main asteroid belt. You collapse all of that down into a point. Now you can see the orbits of the giant planets again and the Kuiper belt. And you collapse all of that down to a point, and it's immersed in the Oort cloud, which is this spherical shell of radius tens of thousands of AU. So curiously, the objects which are currently the furthest from the sun stored in the Oort cloud, they actually formed, as we said, in closer to the sun than the objects that formed in the Kuiper belt. So when Kuiper belt comets come in, we're actually studying potentially things that formed in more distant, colder environments. And when Oort cloud comets come back in, we're studying things that formed near the current distances of the giant planets. Okay. This Oort cloud is actually the thing which more or less defines the scale of what it means to be our solar system. So here's another, this is a cutaway diagram looking through the Oort cloud here. The Oort cloud's about 100,000 astronomical units in diameter. The nearest star is about 2 to 3 times further away than the scale of the Oort cloud. And in fact, the Oort cloud goes out to as far as you can to orbits that basically can remain bound to the sun. Okay, so it truly is the edge of our solar system. So a typical comet will live in the Kuiper belt or Oort cloud reservoir for billions of years. Some gravitational effects perturbs that orbit. And in that process, you lose many of the objects from the solar system. But some small fraction of them enter the Jupiter family, enter the intersolar system and become active comets. Okay, many of them are a branch that are called Jupiter family comets because the ones from the Kuiper belt are often very tied to the orbit of Jupiter. Then they light up. So that's birth. That's how they get to birth as an active comet. How do they die? Well, they can't keep evaporating ice forever. The ices get evaporated away in the near surface environment. And once you evaporate the ices from the upper tens of meters completely, the comet will basically have a crusty shell of rocky material that doesn't vaporize as you heat it, overlaying the rest of the ice rock mix that is the comet that's not accessible. So we think it will take tens of thousands of years for a given comet to evaporate like that and become extinct. Okay. On somewhat longer timescales, anything which is crossing the orbit of Jupiter in our solar system is doomed to be ejected back out into interstellar space on timescales of a few 100,000 years. But that timescale is usually longer than the evaporation timescale. So we think, and we've located some objects that we think are extinct comets. Okay, so let's just quickly turn to this recent apparition of a comet NEOWISE. So I told you that comets are named after discoverers. In this particular case, the discoverer is a spacecraft. WISE is the Wide Field Infrared survey satellite that was built largely to study galaxies, but was actually also very good at scanning the skies. So after its main mission was over, it was rededicated to study near Earth objects, which is the NEO. And so it's called NEOWISE, the mission now. And this comet, which got this interesting little phone number, which planetary astronomers use to uniquely label their objects, was discovered in March 27th of this year. Like Halley, it's on an orbit that's retrograde going around the sun. So here we're looking at a picture tilted at an angle here. So this is the circular orbit of the Earth that we're viewing a little edge on from above the plane. All the planets are going counterclockwise as we're viewing them here. And this comet came from swooping below the plane because it's inclined, and it's going backwards, and it went shooting up into the northern hemisphere and then crossed over above the orbit of the Earth and headed off away from the sun. Okay, so the closest approach to the Earth was actually on July 23rd, when it was up here above the plane of the solar system, about 7/10 of an astronomical unit. So again, this distance from the sun to the Earth is 1 by this definition. So this is about where it was closest to the Earth. And then as it continued along, the Earth was going this way. They actually got further apart. The perihelion was back over here when it was closest to the sun. That's what this yellow line is, marking where the perihelion is. And so when the comet was closest to the sun and the most active, it was further from the Earth. And this wasn't a great geometry either. It was better than many, especially for northern hemisphere observers, compared to the last decades. So if you were watching in the press, there was a fair amount of advertising about this. So especially for us northern hemisphere observers, it was in early July that it was visible in the evening sky, moving to the west, just a little bit south of the Big Dipper, at relatively low altitude above the horizon because of the way the Earth was tilted. But visible to the naked eye if you went out in the evenings. Okay. A lot of people were phoning and saying, what type of telescope should I go buy to see this? And because the scale of these objects is so large, in fact, cometary tails are best viewed without a telescope. You can just go see them naked eye. Binoculars that have a wide field are very good because they give your eye more light gathering power. It's not so much the magnification. You don't want too much magnification. Or a moderate camera with a tripod and long exposure can give you excellent images, as I will show you in a few minutes. Okay, so you don't really benefit much. There's no reason when you're talking about comets to go stampeding to your local telescope to see the comet. Okay, so this was actually the first naked eye comet I had ever seen in my life. This is just at the Prospect Point parking lot in downtown Vancouver in Stanley Park, looking north over the North Shore Mountains in West Vancouver there. This is just a 1/3 of a second exposure with my Android smartphone. It was very easy to see naked eye once you knew where to look. Okay. Luckily, a couple of weeks later, I was in the interior. So I was in Caslow, BC, where the sky is a little bit darker than looking over West Vancouver. Same, just with my smartphone, a longer exposure. So you can see the stars are actually trailing a little bit here due to their motion during the exposure as the Earth spins. Okay. This is a much more impressive picture taken by a colleague of mine in the physics and astronomy department, Mark van Romstok, who's a string theorist, so has no special training in astronomical instrumentation. This is just his 35mm on a camera and on a tripod that was taken at a very dark camping location north of Pemberton. And so the dark sky was really important. And as you can see, there's a very wide field of view here. So this is just a straightforward few second exposure on a tripod. And you can really beautifully see the ion tail here and the curving dust tail of the comet. And so clearly the sun is almost directly below this. The ion tail's pointing back towards it. This is just after sunset as the comet is sinking towards the horizon in its motion across the sky. Okay, so I will stop there. I hope that was interesting, and my understanding is I'll be asked questions via chat through that have been put into chat and moderated by Dr. Yan. Thank you.
Okay, thank you, Brett. So there are some questions coming in on the chat box. One question is, do comets grow back in size after they orbit around?
Right, so you might think if they go back out, maybe they could collect material, but currently in the solar system, the density of material in interplanetary space is so negligible that basically the comet just freezes out and awaits its next return to the sun to heat up again. There's nothing available to collect. So they don't grow anymore. They're just a steady process of evaporation with each subsequent apparition.
Okay, second question is, if a dirty snowball were to slam into the Earth, would it be relatively harmless?
Right, so you might think that an asteroid, a rocky asteroid that's a kilometer across slamming into the Earth, clearly that's going to be a bad day. You might think that perhaps a snowball of that same size hitting the Earth's atmosphere would disintegrate due to atmospheric friction. And the answer is not really, because the impact speed of the comet's going to be something like 30 or 40 kilometers per second. So passing through the entire atmosphere of the Earth will only consume a second or two. And there's no time for the atmosphere at that scale to really do anything. It's just like being struck by a hammer, and it will be just as dangerous. Really, all that matters is the amount of kinetic energy in the impactor, which depends basically on its mass and velocity. At very small scales, like those interplanetary dust particles that I showed you that are millimeters across, those very fluffy particles at that scale, they do get decelerated softly by the Earth's atmosphere. But once you get up to scales of hundreds of meters or bigger, the incoming object doesn't even know the Earth's atmosphere is there. It just passes through it with no slowing down.
Okay, a third question is, I heard that there was an extrasolar comet that was observed recently. Can you say something about that?
Right, so in the process of building our Oort cloud, it's quite likely that as many comets were ejected from the solar system as were kept in the Oort cloud. So when a planetary system forms, as the planets in it eject material, trillions of comets are likely ejected out of that forming planetary system, and they escape and find themselves in orbits around the center of the galaxy, like all the stars nearby us. And it should be possible, and over my entire career, people were wondering why we haven't yet seen a comet that was formed around another star fly through our planetary system. Now, it's not trivial because the space between the stars is so incredibly vast, and the region around our sun where a comet would light up and announce its presence is so tiny that you actually have to wait decades. It depends on how effective astronomy is at surveying the entire sky at great frequency. So it was about now that people were saying we really should have seen one of these by now. And in fact, there were 2 interstellar interlopers discovered just in the last couple of years. One was an object which was not a comet, which is called a Muamua. That was a rocky object. And the second object looked more or less exactly like what we were expecting. This is the comet Borisov, and it flew through our solar system, lit up as a comet, and then exited at high speed. It will never come back. And we're not able to tell where these objects came from. So this was an object that was formed in another solar system, escaped, and was lucky enough to fly through close to our suns for us to observe it.
Okay, so maybe one more final question. Will there be another attempt to land a spacecraft on a comet and retrieve a sample?
Likely. There are no approved missions to do this. There are a couple of missions right now that have just sampled near-Earth asteroids. So I showed you a picture, one of them, called Bennu. So that a NASA spacecraft has sampled that. There's a Japanese spacecraft which has sampled another near-Earth asteroid. So there will be a desire to do that again. Because comets come through the solar system very fast, it's harder to have the opportunity to match speeds with one, pick up samples, and get them back to the Earth. But I'm sure that will eventually be tried again.
Okay, so another question just came in. Is there a reason that any object will orbit in a certain direction around the sun, counterclockwise or clockwise?
Right, so if I back way up here, okay, our protoplanetary nebula, when it collapsed, it happened to have by chance a particular sense of rotation. And therefore that explains why all the planets that have formed out of this spinning nebula and all the objects in the Kuiper belt, if I go here, right? So everything in this picture is going around the sun in this counterclockwise sense, viewed from this direction, because that's the direction that our nebula happened to spin. The Oort cloud comets, when they get ejected out very, very far away, so here in this diagram here, we've got a picture of an object which is going out really far away. All of the perturbations that they then suffer from passing stars basically scramble their orbits. That's why the Oort cloud is a sphere around our sun instead of a flattened structure. And in that scrambling process, half of them have flipped to going backwards and half of them are going forward. And so when they come back into the solar system and become comets, they can be going in both directions. So comets that come back from the Oort cloud are so-called isotropic. They come in with orbits with every orientation.
Okay, so I don't see any other questions, so I think we will end this lecture here. So, well, thank you, Brett.
You're welcome. I hope it was enjoyable.
So, members of the audience, I welcome you back for our next Saturday morning lecture on December 12th.